It's the last week of process. I sent you guys email on what to expect about last due dates. Is that very clear? Is that all fine? I do accept that it's a little, I'm just throwing it on you guys, whatever I'm not able to finish. I'm sort of superficially throwing it on you. I do understand that it is not easy to grasp everything in the limited time we have. But at the same time, I wanted to justify in a very limited form the expectation from the course also. So that was the purpose. I do give a link, or I give reference to set 19 or set 13, which pretty much is the solution to the homework problem or the take-home final exam. So go over it, and I am available for help. Do whatever you can, and I won't, how about this? I expect you guys to do it, but at the same time, I won't assess you too much completely on that. I would do it partly because so that I want to encourage you guys to finish it. If I say no assessment at all, then it is very easy for you to not do. So I would encourage you guys to go through it, but don't stress yourself too much. I think that's one way to put it. And if there is another course that requires your attention more than this, that's a good choice to make. I will say that pick something else if it is more pressing. Is that clear? I don't know how else to put this. We do have the final exam. So there will be 3 questions. Is that what I said? 3 questions? Yes. Yeah, 3 questions which will be relatively straightforward. So, but it requires you to prepare for the final exam. So it will be a test on how much seriously you did your homework. Like that's it should be very. If you did your homework very carefully, it should come out very straightforward. So yeah. So the main thing I would say is that there is a final exam. 3 questions. That's the main thing that's remaining. So final exam, 3 questions, right? Not the take-home one. That's on and the final exam take-home part, you have to do everything and bring it with you to the exam. Is that very clear? That's not usual. Typically, you give a take-home, you take it home and then bring it. So here it is take-home in the sense that it's already provided to you. You bring it to the class. Maybe it should be called something else. Bring home. Yeah. Okay. Okay. Any questions on what is remaining in the course? There's a lot seems to be remaining.
So the 3 questions, last question I think that is from eigenvalue and eigenbasis. Does it cover angular momentum and
No.
complex number, eigenvalue, eigenvector?
Correct. Yeah. First one I said is what, vector calculus, I suppose. Yeah. Something straightforward on vector calculus. Second is simpler, like something that you can do it in 10 minutes if you were doing everything, which is how it is, but sometimes it can be hard also. I do understand that. And eigenvalues, not angular momentum, something that we did, like the U cube is equal to 1. That is a lot of getting used to with the idea of eigenvalues and eigenvectors and the basis more than eigenvalues, eigenvectors. I think we see it in various places. What apparently is not stressed too much is the dependence on the basis. Instead of thinking of a matrix always as 1, 2, 3, 4, 5, that's it, basis dependent quantity. So independent, well, what are the properties that are independent of the basis? Is that clear?
Yeah.
Yeah. So that's what we were doing. Okay. So yeah, I would say that, yeah, you guys don't have time, so I cannot even suggest things how to. Yeah, I think the homework is sufficiently long. What I was going to say is that if you get a chance to read Dirac's book, but I won't say it for the exam. In general, Dirac's book is worth reading, and try to go over like first 4 chapters is basically the basics of quantum mechanics. So that's what reading sometime in whenever you're studying quantum mechanics. That's the way I would. Okay. So
I have another
yeah.
question. In the homework 10, there is J square and the operator. So in that H bar, can I consider H bar equal to 1 and solve it?
Sure. Yeah, but be consistent. Okay, don't like H bar. See, setting H bar equal to 1 has advantages and disadvantages. Advantage is that yes, there's less clutter if you want. That's the biggest advantage you have. But you lose the dimensionality. So when there is a dimension, there is a good check on things. Like dimensions really help you a lot, especially when you're doing complicated things. Often, even intuition wise, it helps a lot. And that's something that you will lose when H bar is equal to 1. I know this because I work in a field where H bar is set equal to 1, but I think it comes at a price. And as you get older, I think you see it more, even though it is very fashionable actually to promote H bar is equal to 1. I feel it's good to keep the units. It's almost like saying F is equal to MA. M is all the time there. Why not set M equal to 1? Yes, perfectly fine. There's absolutely nothing wrong in it. Then force and acceleration have the same units, but M is having resistive properties in it. And actually, yeah, that's not a good example. Yeah, not the best example, because H is a universal constant, and one can argue, one can make a very good case for setting H bar equal to 1 over that. One can make an extremely good case, but I think there are small advantages of not setting it equal to 1, which is also reasonable, especially, or maybe here's that for a beginner, having H bar is good. And when you're an expert, when you're doing bigger things, you're not interested in the basic equations, then setting H bar equal to 1 is good, because this is just a baggage thing. So then you don't like that. But as a beginner, I think H bar. So in a classroom, it's good to do. But if you want to set, go ahead. No problem. Okay. Yeah. Okay. Yeah. So it's so basically what I want to do today is that you will be working with the commutation relations in your homework. I want to derive those commutation relations, derive in the sense of general motivation of how transformation in general gives to commutation relations. Like in quantum mechanics, often we have commutation relations, and what is the idea? What's the interpretation? There are various interpretations of commutation relations, at least 3 one can really emphasize on. And here I want to point out that it is a calculus in a sense. It is when you make a change, let's say displacement, you're making a change, like how do you define velocity, like change in X over time. There's a calculus variation part of it. And when you have a transformation in general, then there is operators satisfy certain changes or variations of the operator are what commutation relations are. That's what I want to at least hint on to. It may not come out very clear because we have limited time. So rotation Z is a very good place where you see that. So let's, so we were talking about rotations, 3-dimensional, so rotations And we typically say R3, right? Like rotation in three-dimensional space, whatever we are in. A vector, and there is X. So this is a vector X. If I were to rotate it, let me go slow. Let me revise or review whatever we did last time. Correct? So there is X1 prime, X2 prime, X3 prime is equal to we said first do X, Y, Z, right? So this is equal to the Z. So this is how do you say this? Yeah, so this is cosine omega 3, sine omega 3 minus sine omega 3 cosine omega 3 0, 0, 1. This is a rotation about the z-axis. Rotate it about the y-axis. So this is cosine omega 2 0 minus sine omega 2 0, 1, 0. X-axis is 1. Two. Okay, so this is rotation about the x-axis, very clear, by an angle omega 1. This is rotation about the y-axis, omega 2 and omega 3. Notice the notation, this is negative, and that has to do with the right-handedness of the nature of rotations. If I were to make this omega 3 small, so omega I is going to be set to delta omega I, small angle rotation. In that case, I can do, or I can approximate cosines as 1, sines as delta omega 3. So this will be equal to 1 prime, x2 prime, x3 prime, 1 delta omega 3. This is minus delta omega 2 of 1 minus delta omega 3. And if I remember correctly, this might be off by a sign, overall sign from the last club. At the very end of the club, we said, oh, we want to switch everything. So we changed the sign. So this is with the correct sign. Is that clear? Any questions? This is also equal to x1, x2, x3, which is the identity matrix. When one multiplies with this, that gives you the. And the second piece, I want to write it as minus of omega 3, omega 2 x3. So this is omega 2 x3 minus of omega 3 x2. So 1, 2, 3, 2 is omega 3 x1 minus omega 1 x3, and 3 will be 1, 2. So this is omega 1 3 minus omega 2. You will notice that this is nothing but the cross product. There is a cyclic property of 2, 3, 3, 1, 1, 2, and then the antisymmetric. This leads us to notice that this is nothing but x prime is equal to the vector x itself minus delta omega crossed sub x. That's your rotation. Clear? Questions? Okay, so that's our basic definition about rotation, but now we want to do multiple rotations. And remember this clearly that, yeah, let's do this with the remote, right? I have an orientation, so yeah, let's see, this is in the camera, yeah. Okay, so this is a remote which has an orientation. The mark the red one, it's pointing up, so that's your z-axis. And let me say x-axis is coming towards the camera or towards you guys. So right-handedness sets y to be in that direction. Right? So x cross y should be equal to z all the time. Okay, that's now I'm going to rotate about the x-axis by 90 degrees, and then about the y-axis by 90 degrees. And the sense of rotation has to be clockwise, but that I will clarify as we go. Okay, so x-axis rotation by 90 degrees, that's this, correct? And now rotation about the y-axis by 90 degrees, that's this. And now notice the red button is pointing in the upward direction, so that's flat. Let me restart this. This time I'll do it in the opposite order. I'll rotate about the y-axis first. So y-axis was here, notice, and I rotated it in that sense. So I do this, right? And now I have to rotate about the x-axis. And what I did was rotation here. So I do this rotation there. And notice that I'm pointing in a very different way. So rotation this is basically the commutation of rotation showing up. So Rx times Ry is not the same as Ry times Rx. It's not commutative. That's the matrices do not multiply that way. And we want to do that here. Here we have made only one rotation, but now we want to do this at an infinitesimal angle. One would think that, oh, this is all because it was a finite rotation. If you really had made this tiny, small rotations, maybe you won't see this. No, you will see this, and that's what we will see, that you won't reach the same place. So let's capture this to a certain extent in a diagram. So we have a vector, let's say x naught to begin with, correct? And I make a rotation, which I'll call it delta 1 omega. So that's the first rotation I can make it delta omega 1 also, that's perfectly fine. It's just because I'm very quickly going to talk in terms of kets, and it is easier to put it on 1. This will make the vector x1. Right? It's a small change. So we have a relation about how x1 is related to x0. So put this x0, that's x0, that's x1, and we get our x1. Then I again make another rotation. This time I call it delta 2 omega 1. Okay, and the notation I want to use is, if I have it here, is x2. So this will, this is a vector, by the way. This is x21. So first you make 1 and then 2. I want to now reverse this. So I first do delta 2 omega, which will give me x2. And this is delta 1 omega. And this I will call as x12. And if these two are the same by any chance, the subtraction will be 0. The difference between that will tell us what's the non-commutativity is. That's what we are interested in. And we would like to know how can we reach from this to this. That's our idea. So that we will come to it later. As of now, let's get these two. What we are going to be doing, just to have a complete picture of what we are addressing here. This is very clear. We have a very clear picture of what x naught is. This is a vector in three-dimensional space. I purposely started with that. Anything that is happening in any space for that matter. So the only difference between this and this is also going to be a vector, but typically when we say a vector, we intrinsically mean that this is finite dimension. Like this has this is in 3 dimensions. You might have 4 dimensions, and typically in our cube, these are real elements. The components are real. So what's the difference between this and this? There are 2 major differences. One is that this could be infinite dimension.
Hilbert space.
This is exactly what I mean by Hilbert. So this is going to be a Hilbert space. This is a vector space, right? There are 2 major differences between them. This could be infinite dimension. It doesn't have to be, right? For example, spin is a classic example. It's 2-dimensional, right? The basic spin half has an up and a down, right? There's only 2 dimensions. So you can have finite dimensional also. So this is finite or infinite. So extend this to infinity also. And it's a Hilbert space. Secondly, its components can be complex. Mostly they're complex. In fact, it needs to be complex. And that is what is a significant difference in quantum mechanics, that complex elements allow the interference problems that we see in classical physics already. Like, for example, in simple 2 strings, when they overlap with each other, you have an interference. Here, these are complex numbers, so that gives a richness there, which is not already there. That's my point. So, but the idea is that it has most of the properties already in there. I'll call this 0. Okay. Do the same things, but now instead of delta omega 1, I'll say this is a generator G1, and this leads to 1. And this will be G2. G2, change the order. This is G1. This is Q1. This is 1, 2. And we would like to again ask, what is this? Okay, so that's our goal. Okay. And this is where the commutation relations will show up. This is where, but that will be same thing on left side. Okay, so that's our broad idea of where we want to head to. So let's begin with this. It's clear what's going on. So this is x1 is equal to x0 minus delta 1 omega crossed with x0. X2 is equal to x1 minus delta 2 omega crossed with x1. Substitute this values in. So this is equal to x1 is this, right? So this is x0 minus delta 1 omega crossed with x0. And next is minus delta 2 omega crossed with x1. I have to put this in. So this is crossed with x0. And as a third term now, right? So this is x0 and this is plus delta 2 omega crossed with delta 1 omega cross with x naught. Is that clear? Okay, any questions there? So I substituted this into this. There are two places that shows up. So x1, this one is this, and this gives you, I think, so okay. So that's you reached here now. Oh, did I do this wrong? Not x2, right? This is x21. Oh, sorry. Okay. So I went here and then I reached here. Now I want to go the path to the bottom. So x2 is equal to x naught minus delta 2 omega cross with x naught. The same thing again. So I have x12 equal to x2 now. x2 minus delta 1 omega cross with x2. X2 is substituted. So this is x naught minus delta 2 omega cross with x naught. And substituted again. So minus delta 1 omega cross with x naught. And plus delta 1 omega cross with delta 2 omega. Right, so now I have reached here and here. What's the difference between the two? How is x21 connected to x12? Just subtract them, right? So subtract them. So x21 minus x12. If things were commutative, this should be 0. These two should be identical. And we do see a lot of cancellation. This cancels this. This cancels this. This cancels this. And we have delta 2 omega cross with delta 1 omega cross with x naught minus of delta 1 omega cross with delta 2 omega cross with x naught. If you have two vectors, three vectors, A cross B cross C, A cross B cross C, plus B cross C cross A, plus BC, C cross A cross B. This is called the Jacobian identity, and that's equal to 0. Yes.
Is there any like limitations for that identity, or does it apply all the time?
It's everything usually has a limitation. So, so in that sense, I would say I'm not sure, but it's the best answer I can give to that is that this shows up at various places. Whenever you have an operator, this shows up, including GR, general relativity. Like that's the that's where you build this hierarchy, right? So it comes up there, and it's like the max. For example, Maxwell's equations. When we say del dotted with b is 0, all that can be seen as once you build such quantities, it can be seen as an identity coming out of that fashion. But this is simpler and simpler structures in that spirit. That's the best I would say. Yeah, it is. I would say it's sufficiently general, but I'm pretty sure that there are some limitations to that. I cannot. Yeah, I'm not able to see that.
Thank you.
Okay. Or at least I can say that, yeah, even for operators, that is satisfied. That's the best we could say. Okay. And vector nature has this property. Like vectors, I think this is a good, like if this was a full course on quantum mechanics, just like you usually give this as a homework. The vector product, like the cross product, right? Satisfies, there is a one-to-one connection between vector product and commutation relation. Okay, so commutation relation satisfies an algebra if you want, right? And vector product also satisfies an algebra, and there is a one-to-one connection. So most of the time you can write things, whatever you write in terms of commutation relation, you can write it as a vector. For example, I think the classic example is this. I'm sure you're familiar of this, right? Maybe you're not conceptually, you might not have got enough time to do this, but this is a familiar idea, right? This is angular moment polymatrix satisfies this, correct? You don't have to write it like this. The best, since we already know vectors as a vector. What is J cross J, by the way? Two vectors cross product? Yeah, cross product. I mean, this is a trap question.
Is it 0?
Oh, it's 0.
Yeah, one would say it is 0, right? One would say it is 0. That's how we learn it in classical mechanics. Only when the numbers are your commute, A, B. So here there is a this minus this, right? You have to, yeah, this, it doesn't even commute, like it is not necessary, right? So this is actually not equal to 0 in quantum mechanics, right? This is equal to I, H4, exactly this, J, J, J. Who would have thought that? Right? This relation in quantum mechanics reads this. So commutation in the language of vectors is this. So remember J1, J2 minus J2, J1, right? J1, J2 minus J2, J1, right? First count, 2, 3, 3, 2, right? If omega was the same as X, then you're basically commuting, right? In this case, the second vector is different from the first vector. If it's the same, then you're talking about X2, X3 minus X3, X2. They do not have to commute. Right, so that's a direct connection, and that it's just that we don't see it so often. Is that clear what I said? Right. So yeah, in that sense, the cross products are having all that information in there, so probably helps your fish. Right. Yeah. So if this is the case, we have this 1, 2, and 3, right? So let me write this as so I want the A cross B. I want to relate A with delta 1, B with delta 2, and so on. So this will be A cross B crossed with C. So I changed the sign of this. Yeah, but these are numbers, right? I can actually, so at this point here, these are not operators, right? This is standard numbers. So I can do all this business of here I've done AB across C. So that's equal to A cross C. Right, and plus B cross C cross A. But I want to write it differently. So this is A cross B cross C. I want to switch this minus B cross B cross C. That's just standard simple number. I've here clearly, like here, for example, A and C has been switched. So there's no operator mechanics in here. Very freely move things around. But here, these are rotation transformations coming back in here. If I were to connect the two, what I'm saying is that this is equal to x21 is equal to x12. This minus this is nothing but a cross B. And yeah, and I will actually also say that this is 1. Yeah, no, it's a minus sign, right? Yeah, okay. So this is equal minus of delta 1 omega. That is 1 is A, right? And 2 is B. 1 is A, 2 is B. So this is delta 1 cross omega, delta 1 cross delta 2 omega crossed with X term. So clear? So here, delta this one, what is this equal to? Delta 1 omega cross the delta 2. Yes.
So what identity did you apply?
Oh, this one,
Okay,
right? I said A is,
del 1.
so this is delta 1 omega cross delta 2 omega crossed with X naught, right?
Mhm.
X naught is equal to delta 1 omega crossed with delta 2 omega crossed with X naught minus of delta 2 omega crossed with delta 1 omega. Okay, did that clarify clearly? Right. And there's a negative sign in there because this is showing up on that side, so that's the negative sign. So that helps you capture this, right? That what exactly is but we want to do something on the Hilbert space. That's more. And this is the basic three-dimensional space. Is that clear? Can I proceed? Okay, so I want to do the same thing on the Hilbert space. So let's say X1. Oh, before that, I should say what's a what is G's, right? I can define this G. In general, let's say if I have 1 is getting, I'll operate this on something. So let's say there's a unitary operator applying on S state to give you another state. What I'm actually using here is that whenever I have a rotation in this space, there is a 1-to-1 correspondence between rotation in the coordinate space and the Hilbert space, which is an abstract space, it could be anything. Right? So for every vector, there is a one-to-one correspondence. Then we do that many times here and there. So for a rotation transformation, what is the transformation that connects to Kets? And that's a unitary operator. So that's a to motivate that. That's a whole. It's more of you have to motivate it. It's a pretty much a postulate, right? We will for our quantities of interest, it is a unitary transformation, but it can be significantly motivated and constrained to a good extent. And unitary operators have this feature that it can be written as an exponential of a Hermitian matrix. Okay, so we will write this as U is going to be equal to exponential of I over H bar times G. That Hermitian piece will be your G in there. Okay, so I can call it H also, but the spirit in which I'm doing this is based on Schwinger's work. Like if you like Schwinger gave some lectures on quantum mechanics, and these are based on that. And his lectures are compiled in a book by Englert. So that's a book like I have followed before. So it talks about this to a good extent. So his notation is to use G. That's a G, and it's a generator, right? So it's a generator of rotation. So that is a good reason to call it G. And in fact, he does this for the whole Poincare group. So it's done in an elaborate way. He even goes to the relativistic part. So it's a good term. If G is small, we are interested in the infinitesimal scenario, then exponential. So if G is small, this is 1 plus I over H bar times G, plus higher order. If G is small, I can truncate it there exactly like infinitesimal rotation. That's what I have. So this is equal to 0 plus I over H bar G times 0 state. And since this is 1, I'll call this U1. So this is G1. So I'm going to 1 using G1. Yes.
So why did you just cut off higher order terms here?
Exactly in the same spirit as this. We are doing infinitesimal rotation. So we are saying that in general, a rotation or a unitary transformation can take you from 1 to a very far place. But I can always reach there by joining a lot of infinitesimal pieces. I'm interested in that variation. Right? I'm building the calculus part of it. That's the main idea. Like, what's the state right next to you? How can I reach there? If I'm talking about displacement or transformation, how do you do the calculus in a Hilbert space? That's what the spirit is. Okay, okay, so this is Q1 now is equal to do the same thing on 1. So this is 1 plus I H bar times G2 times 1. Seems like it is going in the same spirit. So this is 0 plus I over H bar times G1, 0 plus I over H bar times G2 times 0. And finally, IH bar squared, this is plus I over H bar squared times G2 times G1. Good. If I'm following the second route, it is pretty much the same. I just have to swap the quantities. 1, 2 is the same as 0 plus IH bar G2. There we did it in detail, but this is just swapping gives you that. So you don't have to go through that again. One. The difference between the two is 1 is equal to 1, 2. All this cancels out, right? And we have a plus I bar yeah, there is a minus. So let's write this as H bar square. This is G2 comma G1. We will call this variation. So this piece in here, we want to write this as, let me write one more step. Since these are definitions, this is 1, 2 plus, how do I want to see this? Yeah, so let me write this as 1 over IH bar times G1 comma 2. This is a definition now I've introduced, and that's going to be where we have defined 1 over IH bar P1, 2. Like in general, it could be any operation that takes you, right? For a specific scenario, this is a commutation that we will have for rotations. We will do this. So this is equal to what did it do? The definition straight. Q1. Let me write the definition. G. So this was my definition, and I'll write that accordingly. Mistake. 1 over IH bar times G1 comma G2. Is that correct? So there is a IH bar. So whatever is remaining is this IH bar, and there is a negative sign. So that takes care of the opposite. I think it's okay. Okay. So that's my definition. So this is going to be my connection and the Hilbert space. Okay, so that's good. So then basically, if we want to build this, so here the idea is that, okay, what is G1 and G2, right? But now you want to connect it with your delta 1, delta omega. So there's the one-to-one connection going to be there. So what is it you're going to do? So let's go back in here. So it seems like It's just a matter of reading off these things. So the primary connection we have is x prime is equal to x minus delta omega crossed with x. If I can, so the idea is, can I read my G out of this somehow? Can I see this as an operator? That's a basic quantity. After that, I just try to plug this in 1 and 2, label them as 1 and 2. And that's where it's mostly reading it off. So I want to write this as some operator dotted with x, because this will be my ket. Right? X will be my ket. I want to read this off as an operator. First of all, I should have an identity there. So this is going to be my identity. Okay. Think of this as a matrix. Yes.
I'm sorry, how did you know that? How did you know you needed an identity?
Because I want x, right?
Oh,
This,
of course, okay.
right? 1 dotted with x will give me like my x, right? And I want to put something in here instead of a cross product. And what I will do that for that piece is I can introduce a 1 here. Right? So this is, I'm going to read this as delta omega crossed with 1, because I want to see this as a matrix. To compare it with the Hilbert space, I want to see this as a matrix. Even though it is a vector equation, I want to see it as a matrix. Is that clear? So I can visualize this in this manner. So now that's a matrix, and it's nothing new. You've already seen this, right? So this is 1, 0, 0. This is how we built it. Right? This is your 1, and this is minus of delta omega, right? I think if you go back, this is your 0 delta omega 3 minus delta omega 2 delta omega 1 0 0. Correct, if I'm not wrong, that's with the signs, it is just this. And this is just for your x1, x2, x3. Don't forget that, right? Did I get the signs correct? Right. Okay. So this is just this thing. I'm writing it in that form, but I want it in that form so that I can read it off, read my operators out in a convenient manner. If I want to connect it with this, I want to write this as a dot product somehow. Okay, so not only this, I want to now say that, oh, this is okay, but I want to do something better. Right? So this is minus delta omega, or actually not even minus it. I want to write this as plus delta omega. That's my G showing up now. So let's say, since it's angular momentum, I want to write this as J. And you immediately said, oh, this doesn't make sense. What do you mean? I mean, dot here, and how can you get it in dot product with that, right? But that's how I want to do. So just before I mess up with any notations, no, I want to put an IH bar there also, plus IH bar. Okay. And you will say that now this is nonsense because this is dot product that's here. But that is a save. You can save yourself if you think of this as matrices also. And think of polymatrix. Polymatrix is a vector, but built out of matrices, right? So what you want to think of is, so this is a matrix of vectors. So J is a matrix right? A vector whose components are matrices. So this dot product here is the dot product with this matrix structure. And this dot product is the dot product with the vector structure. Is that clear? No. I'll elaborate on that in a minute.
So you,
Before that,
so when you say it's a vector of a matrix, of matrices, it's like a fourth dimensional.
no. So this is so J here. So J here is equal to Jx in the I direction plus Jy in the J direction plus Jz in the K direction, because these are matrices. Jx, Jy, Jz. Why should they be numbers? They're matrices. That's what I mean. Okay. And once they're matrices, they can dot it with this without hurting this. This dots with a vector. This matrix dots with another vector. Is that clear?
So is it similar to the Levi's Zeta? Kind of, where the I to the
Yes.
Okay.
Yes. I'm going to build this in terms of Levi-Civita, so I think you're seeing through that. But be careful.
I was visualizing the.
There is a because that's what I'm going to do in a minute. So probably that's what you're trying to say. But the best is polymatrices. Polymatrices, this is sigma x, sigma y, sigma z. They're matrices, right? That's the best example, right? But they're components of a vector. Okay, so they can act on a column vector. This is the column vector. It turns out to be a vector itself. So this is also a vector, this is also a vector, but they are different spaces in a sense. All right, so be careful with that. Okay. Now, since you said Levi-Civita and there is a confusion with this dot product, so let me clarify what this dot product is. Right? So for that, indices are the best. Let me say this is x. So yeah, let me say x prime I is equal to, and this will be xi plus I over h bar. These are dotted, so I will say delta omega m times jm. Okay, this is this dot product, but this is also having a dot product with this, but this is a matrix, right? Matrix has two indices. The two indices will be I want to put this down steps. Okay, this is M, and this is I, J, and now J has to be summed. That will sum with this. Is that clear? This is the vector index. Hide this, and that's vectors. Right? That's the two vectors. But J's, I said, are matrices. That's your matrix index. And those matrix indices can dot with a vector. Right? And remaining is I is free. Yes.
How to get the J here?
Oh, this is an input. Oh, is this equal? Yeah, I'm saying, right? So that's a definition. Let. So this is a definition. So there is a connection between this and that. That's what I want to read out. So whatever J is supposed to be this. Right? I want to write it in like that because I want to identify my G's.
So is the J angular momentum operator?
Yes, exactly. That's why I'm calling it J now, but it's not clear at this point what it is, right? At this point, I'm just saying there is something operating on this, right? I'm going to call this the angular momentum generator.
Okay.
or the angular momentum operator. That's what it's going to come out as. But clear at this point, it is nothing, right? This is where this is surely correct. From here to here, I'm saying that I want to write this in this form, right? So it's not clear yet. Is it possible? Okay. So I go back here now, and I want to write this in this form. I want to write this as a dot product, right? That's what is necessary. Let's go back now there. So let's write that also in index notation. So that's x prime I is equal to this one dotted with this. That's clear. So that's I. That's innocent thing. So this is minus. This is now a vector. There is an identity, and then there is an x, right? So I'm going to do this. That is the cross product. First of all, this is epsilon. That's a free vector also. Right, so that's I. And I think of, so this is your like this. M. I want to J, yeah. So M goes to this. And hopefully this is correct. Okay. Give me a second. Write this here. Delta omega M delta J K and there is epsilon I M J. Okay. So I explain this is delta omega M times delta JK. Notice this is 1, right? So that's a cross product. A cross product of M and J, A cross B, right? So that's A cross B, but then this vector is free still, so that's your K. That's dotting with the third one, so that's your XK. That help? Yes.
So the delta comes from the identity.
Oh, that's identity. Yeah. In index notation, this will be equal to delta Ij. Right? Because only when it's components, only when I is equal to j. So in component form, that becomes delta Ij. Clear? Yeah.
And is that supposed to be a vector on the left side there?
Yes. Oh,
Okay.
No. Let me remove that. It's yeah, that's unnecessary. Thank you. The moment there is a Kronecker delta, I can collapse this. This survives only when j is equal to k. So I can replace j with k or k with j, either way. So this is equal to xi minus epsilon I m j. Let me rewrite this in a certain way. So this is delta omega m, and I'll replace k with j. So this is epsilon I m j and xj. So most of what I did earlier is a motivation. The basic idea is just to get the identify your generator. Now connect the two. Here now there is a clear connection. This is this with IH bar, right? With the negative sign. M, J, right? And just that M, I have to lift it up in 3 dimensions, going up and down. Is that clear? So, if you allow me. 7 minutes remaining of the last class. And so I have J M I J is equal to H bar over I minus H bar over I times epsilon I mg. Is that clear? These are the components. I and J are the components of a matrix. M is the label of the matrix.
What do you mean by level of them?
There are three matrices, right? J1, J2, J3, sigma X, sigma Y, sigma Z. That's sigma 1, sigma 2, sigma 3. These are the components. Is that clear? So for example, let's say J1. I will not even write Ij. Ij is the indices. Right? As a matrix, this is equal to minus H bar over I. Right. Ij, right? 1, 1. So this is already 1. So this is 0. Right? This is already 1. Let me write this as. So this is epsilon I1j. This survives only 2 and 3. Right, so this is equal to minus H bar over I. Only when 2 and 3 is so 1, it has to be 1, 1 and 2 and 3. 1 is component 2, 3, 2, 3. So this is 0, 0, 0, 2, 3. So 0, 0, 1. This is 1, 2. So 3, 2. So this is 3, 2. So this is 1 and minus 1. That's kind of how I did it. If this is 1, J is 2 and I is equal to 3 is what will be positive. So that's 3, 2 component. 3, 2 component is positive. The other one is antisymmetric. Yes.
I'm sorry, can you say that again?
Okay. If epsilon, so this is 1, right? So I, 1, J. That's the only thing that will survive. So the only thing that can survive here is 1, 2, 3. That's the positive one. So that's 3, 2 component of it, because 1 is just the label of the matrix itself. So that's 3, 2 component, that's 3, 2 component. The 2, 3 component will be exactly opposite, because if I switch it, minus. So one can read out. So that's your J1. J2 is minus H bar over I, epsilon I 2J. 2, so this is minus H bar over I. So 2, so 1, 3, right? 1, 3 is positive, so 0, 0, 1. Okay. And J3 is equal to minus H bar over I, epsilon I 3J. H bar over I is 3, 1, 2, 1, 2, 1. So it's 2, 1, 0, minus 1, 0. That's it. So now you have proper matrices. Once you have this matrix, it's a question of what algebra does it satisfy. You do this, you do all these components. Equal to what? Right? It turns out this is by checking. Now that you have this, you can multiply this, right? J1, J2, J3, do this. And since we are having limited time, I'm claiming that this is epsilon I j k j k. Okay, I haven't shown this, right? But once you have this, it's just a matter of multiplying. But any space, any three quantities that satisfies this algebra will be called angular. Any Hilbert space, anything, any space where you can construct three operators, it satisfies this is angular moment. Even though I started with rotation matrices, I can, anything that does this is going to be angular moment. And this basically identified this J12. Right? This was a definition here. Now we know that this is JK itself, epsilon I, JK. Right? In general, this could be anything. We said that this is J1, this is J2, and this is, now I know what this is. And now I have specified that. Otherwise, that is a very generic statement. Yes.
The generators,
Mhm.
when we're talking about going from like one vector to another vector, you're using generators because of the unitary
Yes.
trace.
Exactly. And the connection here, I didn't emphasize this too much. GI. So when I say G is actually equal to I over H bar times delta omega dotted with G. The way we have said it, there has to be some variation in there, right? This is the coordinate quantity, and that's your J. So this is angular momentum. This is the variation in the coordinate, if you want, and that's the generator, right? And this language changes from books to book. I'm just following up what Schwinger has said it. Often you will see languages where this is defined as a generator, right? J itself, but it's an operator. Yes.
So does it mean that J, I mean the angular momentum is the generator of this transformation?
That's correct.
Start to
Angular momentum is a generator of rotation in this sense. Yeah, here it is rotation, and then you have to say what are the kinds of transformations we talk about. Hamiltonian is the transformation of time translation. Momentum, linear momentum is the transformation of spatial transformations, and then there is a boost operator, and spin is inbuilt inside the angular momentum. So all this has an algebra, and you can find commutation relation between all these operators. Spin, angular momentum, linear momentum, Hamiltonian, and the boost operator. So all this form the Poincare algebra, and you can find the commutational relations. And Schwinger does a complete part of this. He does the whole algebra there. And so I'll encourage you guys to at least like flip through the pages of that. It's a good exposition.
this book, Angular book.
Angular's book, yeah, exactly. That's where he does it at the graduate level, and in a very nice way he does it in his own book. It is called Particles, Sources, and Fields. Particles, Sources, and Field. It's a little more dense, like in the sense it's an advanced textbook. It's a quantum field theory textbook. But this is done in the first 10 pages. So it's an introduction. So it's a very good exposition.
I have one more question. So when we were doing the generators, we only focus on like this G1 and G2, but we could have extended it further, right?
In principle, but typically most of the information comes out of G1. Like it's a commutation variant. Go this way, go that way, and commute it. That's what we are interested in.
So I kind of missed the connection between that and then formulating this in the top left corner.
So the idea here is that, okay, I'm interested in what G12 is, correct? So this is once I know G1 and G2, but what is this? It's not very clear what this is, right? So for understanding that, I take a specific case, the rotation, and go back to my usual rotation space. There I know what this is going to be, right? And that's going to be this, right? But once this is going to be this in this space, it's going one-to-one mapping, right? And then I come back on this space and I say that, oh, that's going to be the same here, because that's a definition of a mapping, right?
Left hand side of this equation is equal to the right hand side.
Correct, exactly. This is this epsilon, exactly. So this is my, sometimes you call it the group. I don't know what that's, you will give it GIJK. In general, it could be anything, right? Here, there are only 9 surviving terms, right? 9 out of 6 out of 27, I think, that are surviving. But in general, that could be 27 terms. So this is a very specific case. So that answer. Again, it's very short introduction to all this, but surely it did not do justice to the whole thing. But yeah, that's an attempt. But thank you for listening. Yeah.
Thank you.
End of the course. Yeah. Okay. Yeah. Good luck. And don't stress about the exams.
Easier said than done.
Yeah, I know. If at all it helps, I always say that I would have failed my own classes if I were a grad student.